Welcome to the Explainer. Okay, today we are unpacking a truly massive engineering feat. We're looking at the new MiniMax M3 model, and specifically, we're going to demystify exactly how the vLLM engine manages to serve this absolute beast on day zero. I mean, we're talking about a model equipped with a staggering 1 million token context window that seamlessly handles multimodal reasoning. It is an incredible capability, but let's be real, it's an absolute nightmare to serve efficiently if you don't have the right architecture. Luckily, the vLLM team has cracked the code, and we're going to break down exactly how they pulled it off. So, here's our roadmap for today. 1. The MiniMax M3 era. 2. Decoding Sparse Attention. 3. Inside the vLLM engine. 4. Unlocking peak performance, and finally 5, the road ahead. Let's just dive right in. All right, section 1, the MiniMax M3 era. The types of workloads that are becoming normal in production are fundamentally changing. Just look at that number, 1 million. MiniMax M3 supports a 1 million token context window. And look, this isn't just some party trick. This is specifically designed for the heavy lifting of modern AI. We're talking about ingesting massive code bases, reading entire document libraries, running complex multi-turn agentic workflows, precise tool use, literally the whole shebang, all in a single prompt. But that massive scale brings us to the elephant in the room. It's the critical engineering question: how do you serve a 1 million token context without completely melting your GPUs? Seriously, if a standard model tried to read 1 million tokens densely, the memory requirements and compute time would just flat out break most production systems. So how does vLLM actually do this?
Well, that brings us to section 2, decoding sparse attention.
The absolute game changer here is MiniMax Sparse Attention, or MSA for short. Conceptually, it's kind of like navigating a gigantic library. If you have a specific question, you don't read every single book on every single shelf, right? That would take forever. Instead, MSA acts like a highly efficient librarian. It's this hybrid design that scores 128 token chunks or blocks of memory. It figures out which blocks are the most relevant, selects only those top blocks for each query, and then runs grouped query attention strictly over that curated selection. So you keep that long context understanding you want, but you massively cut down on the compute. So here is the exact step-by-step for every single query token. First, it scores those candidate KV blocks or key value blocks using a really small specialized index head. Second, it selects the top blocks while applying some hard rules. For instance, it always makes sure the local window block right near the query is included. And third, it runs online softmax attention over only those selected KV blocks. It basically guarantees that the model is only spending precious compute on the data that actually matters for that specific token. Moving on to section 3, inside the vLLM engine. Now, one of the things that makes M3 so incredibly powerful, but honestly a total headache to serve, is its native multimodality. The model doesn't just treat image and video inputs like an afterthought or some separate sidecar process. They are seamlessly integrated right alongside the text. And because of that, the vLLM engine has to effortlessly juggle totally different types of data structures in real time without skipping a beat. To pull this off without bottlenecking the whole system, the vLLM implementation relies on a very strict upstream multimodal pipeline. Think about it. Downloading media, decoding frames, resizing images, creating patch tensors, all of that is incredibly CPU heavy. If you tried to do that on the GPU, you'd be stealing precious processing time away from the actual AI generation. So, vLLM ensures this media preprocessing happens completely upstream. It only passes ready-to-run tensors directly to the GPU worker. Keeping this out of the GPU critical loop is absolutely vital to maintaining that blazing fast inference speed. Which leads us perfectly into section 4, unlocking peak performance. I absolutely love this quote from the developers, and I want to anchor our performance deep dive with it. Do not spend more time deciding which blocks to read than you save by not reading all blocks. It's basically the golden rule here, and a nice mental breather before we get into the heavy math. Basically, if your fancy sparse selection process takes longer than just aggressively reading everything, well, you've completely defeated the purpose. Every single optimization is measured against this rule. Let's look at how they actually apply that rule during the prefill phase. In a standard query major schedule, each query fetches its selected blocks from high bandwidth memory individually. This means the exact same memory block gets moved over and over and over again for different queries. It's incredibly inefficient. So vLLM flips the script to a KV block major schedule.
It organizes the work around the memory blocks themselves. It loads a block into memory just once and then reuses it across all the different queries that need it. For a massive 1 million token prompt, switching to this schedule drastically cuts down on memory movement and speeds the whole thing up. They've also turbocharged the generation phase with day zero support for Eagle 3 speculative decoding. Normally, verifying guesses from a smaller draft model forces the engine into this really slow fallback state, but the vLLM engineers bypass that entirely. They integrated Eagle 3 directly into the decode indexer using specialized split-K kernels. It keeps everything incredibly fast, even when you're processing small draft batches. No slow fallback required. And on top of that, we have these critical kernel fusions. You know how in GPU programming, every time you launch a new operation or kernel, it takes a tiny bit of time. Well, by fusing small operations together, like combining normalization, position encoding, and the KV cache insert into one single step, you massively reduce that launch overhead. They've also cleaned up the quantization paths for the MXFP8 mixture of experts weights. Fusing all these operations keeps those round trips to the high bandwidth memory to an absolute minimum. All right, final section. Section 5, the road ahead. So what happens when you put all this theoretical engineering to the test? You get some seriously impressive validated performance data. On a B300 GPU, the GSM 8K strict accuracy holds strong at 91.51%. The throughput on ShareGPT is pushing over 8,500 tokens per second. And check this out. With speculative decoding turned on, the time per output token drops to a mere 9.04 milliseconds. That's insanely fast. It proves that all these complex sparse attention mechanisms actually translate to blazing fast, highly accurate real-world performance. But wait, it actually gets cooler. The impact of this goes way beyond just serving end users. This rock-solid serving infrastructure is actually doubling as the rollout engine for reinforcement learning. Right now, NVIDIA's NeMo-RL framework is running MiniMax M3 post-training, and they are natively using vLLM as the generation backend. When an inference engine is this efficient, it literally accelerates the model training loop itself. That is a huge deal. Looking forward, the vLLM team is absolutely not slowing down. Their roadmap includes upcoming features like FP8 indexer and KV cache paths, which are going to squeeze even more batch capacity out of the memory. They're working on context parallelism, so those massive long prefills can scale across multiple different machines. Plus, they're expanding disaggregated serving recipes and pushing for even further multimodal gateway optimization. Bottom line, this engine is only going to get faster and more capable. So I want to leave you with a provocative question. What extreme long context workloads are you going to build now that a 1 million token window is actually practical in production? The old engineering barrier of melting your GPUs, it's gone. The infrastructure is here, it's open source, and as we've seen, it is incredibly fast. The only limit now is what you decide to create with it. Thank you so much for joining me to unpack this fascinating source material, and as always, keep building.